Now it seems to work. Oh, okay. Yes, I can see something on YouTube. Okay, so now we can get started, and I think you should already see the screen of my presentation. I'm not sure you want to see me as well, but all right. Okay. Can you share here the YouTube link? Yeah. I need to find out myself where it is. Mm-hmm. If anybody has any clue where this link is, I'm very glad about any kind of feedback. Because in the Jitsi description, it looks quite different from the current interface at YouTube. And in general, yeah, doesn't work at all. In general, this RTTPM link, which is replaced by a smiley in the chat, should be the URL, but there is no other URL I can give to you, so I'm not sure, even though it says the privacy settings are set to public. So that should be fine. Okay, 2 more minutes, but then I will try to search it in 2 more minutes, but then I will start for sure. Yeah, I found it just in time. So in the chat, you can see the URL for this live stream. It was at the top right corner and behind an icon. Okay. So, all right. So welcome to this month's RustGraz meetup. And we're going to talk about I/O, which generally stands for input and output. So as usual, I'm going to give a short prologue first, where we discuss the issues the open questions that were left from last time. And then I will also want to talk about the Mozilla layoff that happened this month. Okay, so the first question is, what is the relation of MSPC channel of Rust and compared to the channels given by the Go programming language? Because we've been confused, okay, in both cases you can send and receive data. So here we have the method send and receive is written RECV. These are methods you can use on both channels in Rust. And this is very similar to the concept in Golang, where you have less than hyphen in order to send some value into a channel and also receive some data via some channel. So where are the differences between the Rust channels and the Golang channels? As it turns out, Rust 1.32 deprecated a select macro, which I think was very much inspired by the Golang design. And there were some designs they regret. You can follow the link here, where they basically said, yeah, currently how we designed it, memory management and the API is not really helpful. And so we need a different concept. So they deprecated this select macro. And they are planning, this is a very initial phase, they are planning to create some MPSC select macro, but yeah, it's still under development. It will take some Rust releases in order to develop. So in conclusion, some way to answer this question is you can send and receive values via these channels, both in Rust and in Go. But on the other hand, in Rust, you can only listen for new values on one channel, whereas in Go, it's possible to wait for the first data arriving at multiple channels. So this is some way to look at it. And there is some third-party crate, which is called Crossbeam channel. And this is the current way to go compared to the MPSC select macro, which isn't available yet, but which will be fundamentally designed in a way similar to Crossbeam channel. So yeah, this is the way to go if you want to use channels in Rust. Okay, so this was a concurrency topic. Another concurrency topic was about...
sorry for interrupting,
yes,
Lucas.
please.
We can't read your slides because activating the video stream again has led to very low resolution on the slides.
Oh, that's bad. Thank you very much for the information. And I'm not sure what's the best approach right now. Since you activated the video. Okay, so it's just about my video, right? Maybe now it improves.
Yes, it's fine again.
Yes.
So.
Okay, thank you very much for the notification. Okay, and the second question I want to answer in this prologue is, what does the atomic in arg refer to? So I was a little bit confused whether it refers to an atomic operation somehow applied to type T, or is it just an atomic operation incrementing the ref counter contained in this arg? And of course, immediately if you look up the description, unlike RC, arg uses atomic operation for its reference counting. So it really refers to the reference counter, which is part of the arg. That is incremented with an atomic CPU instruction. Okay. And the third topic I want to talk about is the 2020 Mozilla layoff, because I think in some way it influences the Rust community. But what are the details? So first of all, about the structure of Mozilla. So we have the Mozilla Foundation, which is an American not-for-profit organization that exists since 2003. And on the other hand, we have a corporation, which is for profit. And essentially all the legal stuff is done by Mozilla Corporation, and the general mission is defined by the Mozilla Foundation, and all the money and the corporation is capable of the corporation receives is basically invested back into the Mozilla project and therefore into the Mozilla Foundation. So that's the way they structured it. And now the issue is currently that in 2018, Mozilla Corporation said it had about 1,000 employees worldwide. And as far as I know, that's still the same until before this month. And Mozilla makes most of its money from companies paying to make their search engine their default in Firefox. So they have huge deals with Yandex and Google, and especially Google is the main financial contributor to Mozilla. And the CEO, Mitchell Baker, said this month in a press release, you may recall that we expected to be earning revenue in 2019 and 2020 from new subscription products, as well as higher revenue from sources outside of search, but this didn't happen. This is also, of course, due to the COVID-19 situation, as they pointed out, and therefore Mozilla is laying off 250 people. That's a quarter of its workforce, right? And plans to refocus some teams on projects designed to make money. So there are some subscription-based products like VPN, where you pay a certain amount of money per month, and they provide you a VPN service, and they try to focus on these kind of services and have less money for the free software projects they also develop. So here I have the link to the press release, and after 9 months making VisiPrint and working on Servo Dev and contributing to RustLang, I'll be looking for an next roles as one of the Servo developers. If you're looking for a senior systems engineer, my DMs are open, and he wrote this as part of the Mozilla Lifeboat on Twitter, which is basically a project which tries to give new job opportunities for these laid off people. And the affected teams are reportedly Servo, Rust, Firefox developer tools, and some others. And yeah, since Rust itself and Servo is affected, that's not so good. Rust doesn't completely rely on Mozilla. It's a community project, and there are just some few developers at Mozilla working full-time basically on Rust or Rust infrastructure, if I remember correctly, like the crates server. There are many people from Mozilla involved in that. But in general, of course, it also affects Rust, and I think especially one of the flagship projects called Servo, which is the parallel web engine used in Firefox these days. So Servo, the parallel browser engine project. There was one issue opened right when the layoff was publicly announced. And basically one of the developers said, yeah, just then, a lot of us don't have the mental bandwidth at the moment to think or plan anything for the future of Servo, since it was also a surprise to them. And so the question is how Servo will proceed, and why is Servo in any way interesting or an important project. In 2013, Mozilla began the experimental Servo project, which is an engine designed from scratch with the goal of improving concurrency and parallelism, while also reducing memory safety vulnerabilities. So these are the two major areas where Rust contributes in some way to programming language design. An important factor is writing servo in the Rust programming language, also created by Mozilla, which is designed to generate compiled code with better memory safety, concurrency, and parallelism than compiled C++ code. So essentially, you have the Firefox web browser running with the Gecko engine. And then Rust was designed, which focuses on concurrency and memory safety, which exactly has the attributes that somehow are also relevant for the web browser. And therefore, they decided to rewrite some components in Rust. And the CSS engine was one of the first, which, to the best of my knowledge, was entirely replaced by Rust in the Firefox Quantum release, which is version 15.7. And just to give you an overview over the different browsers we currently have, so Opera first used the Presto engine, then the WebKit, and then the WebKit fork called Blink. And Blink is exactly the one used by Chrome these days. So yeah, let's go through one of the browser, one after another browser. The Internet Explorer was originally some Mosaic, used some Mosaic engine, which was contributed by Spyglass, a company, and then had the Trident engine over a long period of time. I think, yeah, Internet Explorer 3 is missing here, but they don't have any internal codename for the engine back then. And Conqueror was the original designer of the KHTML engine, and this was kind of the foundation for the WebKit engine, which eventually became Blink. Okay, and Edge originally was initiated in 2015 as successor of Internet Explorer with the Edge HTML engine, and then switched to Blink in 2018. So in some way, you can see that a lot of engines switched to Blink, and also Safari used KHTML first. Started with KHTML, and then you used the fork WebKit. Sorry, first it was initiated with KHTML, and at the same time WebKit was released. So they right after that, in the same year, they switched to WebKit. WebKit was in 2013. No, that can't be right. Sorry. I'm mixing up something here. If I remember correctly, initially it was KHTML, and then they switched to WebKit. And Chromium, yeah, that was the WebKit first, and then they forked it and created the Blink engine. And the main contributor to the Blink web browser engine these days is Google. And in terms of Firefox, we have Gecko and Servo. And Servo is, yeah, basically pushed by Mozilla. And if you look at the current support of, sorry, do I not have the slide here? Sorry. There are, in terms of the web standards, the Gecko Servo stack is one of the successful ones, and also Blink. These are the two leading web browser engines, and now basically we have to accept that Servo is under pressure, and it's difficult to estimate whether a Servo can still keep up with the current web standards. As far as the web standards are concerned, for example, one of the aspects is, as a mathematician, of course, I'm annoyed that the MathML standard developed by W3C is only supported by the Firefox web browser and not by the Blink engine web browsers. So if you want to see, if you want to write down mathematical typesetting in HTML, then you are either bound to use Firefox, and we only have support there, or use one of the JavaScript libraries which kind of composite the typesetting with a lot of JavaScript, CSS, fonts, and HTML. Yeah, so I'm sad in some way that Servo is under pressure, and we will see how they will be able to hopefully keep up with the current development of web standards. Okay, yeah. Sorry, I screwed up my slides here. In general, we should switch to the dialogue here now, which is the main topic for today, which is input and output. And yeah, mainly we are going to talk about files on a file system. So what are files? So from a file system perspective, files are just binary blobs we have. And on the end, how can we find these files? We use file paths. And these file paths, or the base names, which are the components of these file paths, are just byte arrays. So this is important that from a file system perspective, we really only have like bytes here. Everything is just a sequence of bytes. And from a programmer's perspective, we have a different setting. So files are either strings or bytes. So we have various text formats. So we want to read some text file and just do not care about the specific encoding in bytes, but we care about the Unicode string and want to apply various operations on that. Or if it's a binary file, of course, like a JPEG image, that's just binary blob. And we need to write specific libraries which serialize a certain data structure into a binary blob, which can be interpreted as JPEG file. And in terms of file paths, okay, we also need to display them to the user. And now the question arises, okay, I want to display them. I don't want to give them a byte sequence, but more like a string, where we have which is independent of the encoding. So there is a certain gap between what the file system provides and what the programmer wants to have. And we will look at this from the Rust side. And just so you know, if you want to dig into this question, okay, I have a string, I want to serialize it into some sequence of bytes, a vector of bytes. What are the idiomatic transformations? There is one beautiful Stack Overflow post showing all these transformations. And this just gives you a summary. Of course, this is not so beautiful to see. It just also shows how difficult or complex the Rust type system is. But of course, Rust type system is also very powerful and neat. As we will see, I have some examples. Okay. In order to talk about files, one of the most important modules we have in the standard library is standard FS. So these are file system manipulation operations. And these it provides us tools to read files, for example, as we can see in the next slide. So here we want to read an entire UTF-8 encoded text file into a string. How can we do that? So in FS, we have some function called read_to_string, which just takes the file name as a string and then tries to read the entire string into a string object and can either return that one or gives you an error. And the expect method allows you to panic in case of an error. Unable to read file will be the message printed. Or in the other case, we continue with the data variable which contains the string we read, and for example, we can print it out. So this is just a handy function in order to interact with the file system. Okay, and there is a certain difference if we don't ask for a string, but we just want to consider the different bytes. Then we want to read that into a vector of unsigned integers of 8 bits. And we use the function read, not read as read to string, but read. And the way it works is exactly the same. We provide the file path as a string, and then we, upon the return value, we call expect. And then in data, we have this vector of bytes. And for example, for every vector, we can print the length. So these are two functions provided by the standard library. And this is actually, if I remember correctly, like the Rust release 1.26. Since then, these convenient functions are available. And before that, you had to create underlying objects explicitly. Okay, and now the reverse operation, we don't want to read, but we want to write into a file. So we can take a string. Yeah, here we consider the variable data, which contains a string, and we want to write it to a file. So we just call fs and the write function, provide the file path and also the string, and this will be written. If it doesn't work, again, we use expect in order to create a panic in this case. Yeah. And I think considering how little code you have to write to read and write files, that's a quite convenient API. Okay, what's the underlying type? What underlying types do we have here? So these are traits that are working in the background. We have the standard IO read trait, which has a method read, which takes a mutable slice in order to read from it, and then stores it in the object that is implemented. It stores it in the object for which read is implemented. The read trait is implemented. And the result tells you how many bytes have been written. Optionally, of course, because it's a result type. And we also have the write trait, where we have a write method and also a flush method. And write just... Oh boy, I just screwed up the description of the method of the read method, because of course we read the data into the buffer, and the result also tells us how many bytes have been read, whereas the write method we have in the write trait, that one takes the buffer and writes it into the object we consider. Sorry, so yeah, these are somehow, I think, quite intuitive how they work. The flush method needs to be called explicitly in order to flush all the data we want to write, because essentially we can also have buffered input-output mechanisms. So maybe it just writes the data into a temporary buffer, but not actually onto the hard disk drive, for example. So we need to call flush explicitly to tell it, okay, all the data you have in your temporary buffer need to be written right now. Okay, and this is exactly the transition towards the topic of buffered I/O. So considering that we have, for example, the use case, we want to read the metadata of an ISO image file. And such an ISO image file, yeah, in case of Windows 10, I recently had a look on that. It's 5.8 gigabytes. and therefore, yeah, depending on your main memory size you have on your computer, it might not fit into memory. And in these cases, buffered I/O is the way to go. And in case of buffered I/O, we have a trait called buffRead, which has two methods. Essentially, the fill buff method allows you to read some data, but the descriptor telling at which position we are doesn't actually update. That's part of the consume routine. So yeah, these are methods which are very low level and you don't need to use them explicitly. It's just the method that are required to be implemented in order to support buffRead. And the point is that then we have other methods which are provided and quite convenient, such as read a file in a buffered way, but line by line. So each time a line is returned, and that's a quite convenient way. Okay. So in general, we have these traits, and here in the buffered case, we don't have a write trait in that way. So buffWrite doesn't exist, but there is a struct buffWriter, which is as a concrete version of this non-existent trait. Okay, and with that, yeah, in general, we can write in a buffered way, but there is no abstraction for this buffered writing. In terms of buffReader, which is an actual implementation of buffRead, the default buffer capacity is currently 8 kilobytes, but that might change in the future. That's just the default setting for the buffer that you use whenever you create such a buffReader with buffReader : new. Okay, and then how does it look like if we want to read data in a buffered way? First of all, we create a mutable string object, and then we open a file, and this point a buffReader we create with : new towards that file. And then we can call onto this buffReader the read to string method, which actually reads the data into this variable data. What's important here is that the read trait needs to be used. So we import it in some way at the top, but we don't actually address it in any way here in the main function. As I pointed out in previous sessions, it's important to also import the traits that are used, even though they occur implicitly in the source code. So in an intermediate type here needs the read trait, and he returns an implementation of the read trait. And in order to use it and call upon a method on it, then we also need to use this read trait. Yeah, in general, regarding the example, I think it's quite obvious. So the string object allows us to dynamically allocate the string data we need on the heap. And essentially, we open a file, then we wrap it in some way into a buffered reader, and then we ask the buffered reader to read the data into an actual string. I think that's also quite intuitive. The corresponding write example looks like this. Again, we have a buffWriter, and we also need to use the write trait. Okay, so first of all, we create a new file in a temporary directory on Unix, for example. And then we create such a buffWriter and write and use the write or method in order to write the data variable into it. Here we here we have a string in data, but we don't know the encoding so far. And if we just call as bytes, then it will be encoded in UTF-8. I need to point out that here in the methods, you cannot see explicitly that this is UTF-8, but as you might know in Rust, the default encoding is always UTF-8. So whenever we talk about the conversion of some string into bytes, we implicitly or per default, we always mean UTF-8. Okay, what's also very convenient is to iterate line by line. So in the main routine, we can open some file, then we use wrap it with a buffered reader, and then the buffered reader also implements implicitly a method called lines, which allows us to iterate over the data line by line. And the line object we get, this is actually a result type and must not necessarily be an actual line that you consider, but there might be some problem. So we also need to call the, for example, except method in order to create a panic if anything goes wrong. Okay. By the way, what is considered a line actually? So in terms of Unicode, there are various characters which can represent white space, for example. But what is actually a line, considered as a line break? Also in terms of Unicode, I think it really boils down to these two characters, which is hexadecimal A and hexadecimal B. So the carriage return and the line feed characters. And Rust specifies that these lines will occur if you split a string by either a new line or the combination of the carriage return and the new line. So these are the substrings it looks for and uses and applies split in some way upon it. Okay. I also want to dive, so we talked about reading and writing files, but I also want to dive into the question of file paths. So what are file paths actually? And is there any abstraction for it? Because we have certain differences between the various systems. So in terms of Linux, for example, we have the / in order to separate the various components in a file path, but on Windows, it's the \. So is there any issue with this? So can we just specify the / for Windows paths and just the / for Linux? Yes, this is the case. But if you want to denote Windows file paths in Rust, it's quite convenient to use the raw prefix, so use R in front of the double quotes in order to signify that the / doesn't introduce an actual sequence like with X. We can specify a byte in hexadecimal digits, but we want to consider the specific string \x20. This is something that is possible. So it's taken literally if we use the R prefix. This is some best practice for Windows systems. So you can use the \. And if we just write down all the paths in / does it work on Linux and Windows on both systems? The answer is yes. This is just because Windows has a fallback mechanism for this. I don't know whether anything changed. I have no idea about the architecture. If anything changed with the introduction of the Linux subsystem. So if anybody has any background information on that, I'm curious about that. Okay. So now we talked about reading and writing files, and we also considered file paths, but I want to also talk about file formats. So file formats specify the specific layout of the data in the file, and there are various options. So in general, what we are interested in is either data serialization or configuration languages. So for data serialization, I mean like we have data in Rust and we want to write it onto the hard disk drive in order to pick it up later on and continue, for example, our program. So in that sense, just to store some state. On the other hand, we also have configuration languages where cargo.toml is a really obvious example where we want to specify how certain processes need to work when we do some computations. Okay, and in terms of file formats, it's always interesting the question of encoding. So we have these ISO 8859 encodings, which are 1 to 16, excluding the 12, because that one was abandoned apparently. And we also have the American standard for character interchange, something like that. Damn, I don't know it by heart. And we have these Unicode encodings of UTF-8, 16, or 32. And I also looked up, there is some, because I looked at the list of encodings, also there is an OML encoding, which is apparently was designed for the TeX language originally. So it's a 7-bit encoding which can be used inside of the TeX engine. So you have all the various Greek and Latin characters available. That's something I came across when looking at the list of encodings. That's something I didn't know, that there were character encodings specifically designed for TeX. Okay. In terms of file formats, we have a huge list of them, and actually this one is from Wikipedia, even though it's incomplete. ASN, for example, is one a very popular one in cryptography. BSON is a binary format of JSON. Then we also have like message pack is also quite well known, and JSON is very popular because it's a subset of JavaScript and used because it's easy to change information in Ajax cores, for example. There is also the programming languages PHP and Python, which created their own serialization formats. Pickle is the one by Python, and PHP uses the serialize function to serialize any kind of arbitrary data you put in there. And we also have, for example, protobuf, which is a much more modern way to exchange data. We have the AST expressions inspired by Lisp. And we also have, of course, XML, but XML itself doesn't really specify any data types. So Wikipedia lists them as XML/SOAP in order to specify the data types you can send or want to exchange. Okay, and sorry, XML is included in my list, but I didn't. It didn't make it into my slides. So we're going to talk about CSV, JSON, and YAML. These are the formats we are going to talk about today, and I will show you some Rust examples to deal with them. So first of all, we have the CSV format, which is not a formal standard. So there are really some open questions whenever we deal with CSV files. So what's the underlying encoding? Which delimiter character is used? So even though the comma separated values say comma, often another character is used. And actually there was some proposal to rename comma separated values into character separated values to signify that or emphasize this actual situation. And also then we have escaping issues, like if we use a comma as a delimiter, how can we write down a comma in the field inside the CSV file? And can you actually write down line breaks in any way inside one field of this CSV? Because in general, line breaks are only reserved in order to denote the beginning of a new record in this CSV file. We use the file extension CSV, and the MIME type is text CSV. This is defined for this format. And in Rust, we have the CSV crate by the very famous contributor Burn Sushi. There's a lot of important tools, command line tools you can use, and which are implemented in Rust. And he also provides a tutorial. So I assume you're all familiar with CSV files. I put in some content down there. Yeah, it's really trivial. And in the so essentially here the first line denotes a header, and the fourth line shows one string which contains comma itself. So it is escaped with double quotes at the beginning and the end. So, okay, how do you use this CSV crate? So we can create a CSV reader, and in that particular case, we read the data from standard in. In general, it just needs to be any type implementing the buff read trait. And yeah, then we have some handle, some reader, RDR, and we can call the method records on it in order to iterate over these various results. Again, the result itself is a type result, so it might give you an error. So we need to use the question mark to do some error handling. Just to revise quickly the question mark operator, if there is an error contained in this result, then we will make an early exit and report an error as return type, because here again the function has a return type of result, and this is a requirement in order to actually use the question mark operator. So the question mark operator allows you to make an early exit in the case of an error, and in the other case, the actual data will be returned and stored in this variable called record, and we can of course print this record. Here it has a debug representation. Okay, and in the main routine, we can just call this example and take the result. Either it was successful and all the data was printed, so we get an empty tuple, or in the error case, and here we have an if-let construction which only matches the error case. In the error case, we take the error and print it out, and then use standard process exit to exit with the exit code 1. Okay, so this is just the CSV crate to iterate over. And I also want to point out, Burn Sushi developed the XSV command line tool, which allows you to index, slice, analyze, split, and join CSV files. That's very convenient. And yeah, Burn Sushi contributed RipGrab, the regex engine, and these XSV tools, which are very popular in the Rust community. And in general, if you need a command line tool to deal with CSVs, please consider XSV. Okay, now we come to the serde crate, which is a framework for serializing and deserializing Rust data structures efficiently and generically. And this serde crate essentially, as far as I understand, the structure is a kind of umbrella crate for the actual implementations. So there are separate crates for each data type. We have, for example, serde_JSON for the JSON implementation. And the serde is just the umbrella project for that. And we have many supported data formats. Here, for example, JSON, that's I think always the most prominent one when considering serde. Then we also have various ones I didn't mention before, like bin code, cbor, YAML, message pack, toml, pickle, ron, bison, JSON 5. That's also another JSON derivative. And URL, env. What was that? I think env was developed by Facebook, if I remember correctly. And also the format used by dbus is also a data format you can serialize to. Yeah, so this is the serde crate, and I introduced it because now we are going to talk about toml, and we don't use a CSV crate, but an actual serde toml crate, and therefore that's why I introduced serde. Okay, so toml, what is toml? Tom's obvious minimal language is a config file format for humans, and it tries to be a minimal configuration file format that's easy to read due to obvious semantics. And toml is designed to map unambiguously to a hash table. So it should be easy to part that into data structures in a variety of languages. And in general, there is a format standard specifying which syntax is allowed in toml. And for every value in there, you can explicitly point out which type it is. So it's strongly typed, and it's human readable and allows comments. In terms of the file extension, it's always .toml. And the MIME type, is it specified? No, they are still debating it. They really don't know what's the right way to go. It should be either text/toml or application/toml. And when discussing these MIME types, you always wonder about the implications of application or text on the character encoding. That's something very difficult to decide. So you always need some people from the standards committees in order to support you upon that decision. So in general, it's not specified, unlike for CSV, for example. Okay. In general, toml is case sensitive. A toml file must be valid UTF-8 encoded Unicode document, and the white space is defined as tab or space, and the new line, okay, is line feed or carriage return line feed. And in terms of the bare keys that are always the left side values, they may only contain ASCII letters, ASCII digits, underscore, and dashes. And there is one particular syntax which allows you to use more complex, to write down these keys in a more complex way. And we will briefly talk about the data types, then we will look at some pathological examples for a toml file. So the data types supported in toml are the associative array, which is just a key value association. Then we have arrays, we have tables. We can specify these tables also inline. Then we have arrays of tables, and we have integer and floats and booleans. And the most interesting one is dates and times. This is also part of toml. So if a programming language doesn't has any notion of date or time, let's say the C programming language, for example, there is no obvious way how to serialize these. But in general, it's the RFC 339 standard, which is quite common these days. So let's look at one example. In general, we have these key value associations. On the left-hand side, you have a title. On the right-hand side, you have a string called toml document. And then we have the various sections which are inspired by the ini file format. And these, in toml terminology, these are called tables. So types is one table. Here we have a bare key that allows, for example, the hyphen as part of the key name. And we can use, unlike the bare keys, here we have a non-bare key, which uses the single quote in order to begin the key name. it also stops with a single quote. And this way we can also write down more complicated key strings. Okay, in terms of bool, it's really trivial, like true and false. In terms of integer, you can specify them in various bases with the obvious prefixes. So X for hexadecimal, B for binary, and of course, per default, it's a decimal representation. In terms of floating point values, you can use the scientific notation with the E, and also prefixes with plus and minus. And we have an infinity and not a number type, of course, in order to support the complete IEEE 754 standard. In terms of dates and times, we can specify them just like starting with the year. Then we use hyphens to separate year, month, and day. Then we use the T character to separate the date from the time. And optionally, we can also append an offset. In the second example, we replace the T separator with a space. This is also allowed because that's part of the RFC. And in terms of the offset, it's specified by Z that Z stands for Zulu, right? I think, yeah, that's the time zone, the Zulu time zone. Okay, we continue with some more examples in Toml. Here we have a string which also contains escape characters. So, sorry, these are escape sequences in some way. Okay, so we have \t in order to denote a horizontal tab, but we can also write down \u and write 4-digit hexadecimal representation of a Unicode character. Okay, and if you use single quotes, then you can these backslashes do not carry any special semantics and are taken literally. And if you want to write down multi-line strings, then you can use the triple double quote character to begin and end the string. And these backslashes strip all the leading white space in the next line. So the text before roses will be stripped away, this indentation, due to the backslash in the previous line. Arrays are denoted with square brackets, and they can be arbitrarily nested and also heterogeneous. So the first element can be a float, the second one an integer, and the third one a string. That's also possible. And you also see a comment here. It is always a single line comment. So we start with the hash symbol, and until the end of the line, we have a comment. The keys of, the name of a table here, types.inline table, can also be more complex. You just need to wrap the name you want to use in double quotes. Then you're allowed, for example, to also use the space in such a name. And we have arrays, we have tables, and okay, so the final example here, name equals, this is just the inline syntax for a table in Toml. So just like we write down some int and associate some value with it, here we have types inline table dot name, and underneath we have various keys like lang and lock. Okay, so these are all the types of the Toml file format. I wanted to reiterate a little bit upon it. because it's the Rust programming language always creates these cargo.toml files, which are used to configure the crate you are currently building. And yeah, so this is the default format used a lot in the Rust community, I guess. Okay, and right. Sorry, there is one more point. So you can have an array of tables. So if you use the double square brackets, these do not overwrite. So usually if you just use single quotes products and then specify some values, and later on again single square brackets products, then this is in general not allowed, or in some cases the previous values will be overwritten by the latter cases. And if you use the double square bracket notation, you actually append these various values. So you can see the result here. So on the previous slide, we have seen 3 entries for products. So the resulting data structure that will be created has a key products and then contains in an array 3 tables which are corresponding to the underlying values we've specified before. Okay, so yeah, that's the toml case. And now I want to switch to, sorry, why did I screw up my slides here? Sorry. In general, the question now arises if we want to serialize or deserialize it. We want to retrieve the values we specified in a file format, but there are 2 different approaches here for compiled languages. So on the one hand, you could specify the structure and all these contained values in some way, and the deserializer plugs in the values from the file into this specified structure. This is one approach in order to deal with that. That's really neat because you specify explicitly where the memory is allocated and what the structure is. So the deserializer can do a lot of optimizations in order to fill up the data. But on the other hand, we have a problem if we receive some data, for example, via the network, and we don't know the structure of this file yet. So for example, we receive some JSON object via network and we don't know the actual keys contained in there, but we want to, for example, iterate over them. Then we actually need to deserialize this object at runtime and create an abstract representation for it and allocate all the corresponding fields on the heap. So we have 2 different approaches. On the one hand, we specify a particular structure and fill the data in there. And on the other hand, we get some abstract type, which allows us to look up the actual values in there. And I just want to give you one example here in Golang for the former approach. So where we specify the actual structure. So here we have a structure, and on the right-hand side, you can see these fields or tags in some way. So for example, video ID, here we specify that for the JSON parser, it should be the value that is stored in the object with the key video ID. So we receive some JSON object, we want to deserialize it and plug the data into this structure. So we take this object, look for the video ID key, and the corresponding value will be coerced into an integer and stored with the in this field named video ID. Also the same for title and published time text. And yeah, this is the formal approach where we specify the structure and we do not on the fly dynamically read the actual data of the JSON, but just plug in the values we are considering. Of course, at compile time, here we specify the structure, which keys we want to consider, for example. So that doesn't work for everything. And now the question is, if we look at the Toml serializer in Rust, which approaches are supported? Do we have to know the structure beforehand or not? And as it turns out, both of them are supported. So for the first approach, where we specify the structure, we can use such a derive attribute. So first we consider some string, which contains Toml data. In this specific example, we don't have any syntax highlighting because the pigments syntax highlighter doesn't implement it correctly. Here we use the R hashtag prefix. And why do we use that, or what does it stand for? So first of all, we use a raw, and we've seen before that raw allows us not to disable the interpretation of backslashes. So for example, \t stands for a horizontal tab. And if there is some backslash in this Toml file, it won't be interpreted in any way, but taken literally. Okay, and in terms of the fact that we use a delimiter double quote in order to denote this string here in Rust, but also double quotes occur in the in the Toml content, we use hash double quote because that's the actual string starting and terminating our Rust string. So in that particular setting, if you want to write down Toml or any other file format, it's really convenient to use this R hash prefix and then the hash suffix in order to denote, to write down Toml content and not to interpret any content in between the initializer and the finalizer of the string. Okay, so we have in Toml string some Toml content. Okay. Now we use this derive attribute. Okay, first of all, we need to use it. Then we can define some structure. And all these values need to be wrapped with an option because we cannot be sure that these will actually occur in the Toml file that is specified. But in general, we have annotated here the different types, and whatever we read will be coerced towards these types. Okay. Of course, an array is a vector. Yeah, I think it's quite obvious how it works. We also use the debug attribute because we also want to have a debug representation if we want to print it in order to debug our program. Okay, and yeah, so this is the case for config, then also for server config. And please be aware that config contains a server config and a peer config. Peer config occurs in the next slide. And now we can take this Toml str variable we defined before and use Toml from string, provide Toml string as a parameter. Then it will try to take this string, parse it correspondingly, and try to plug all the data into our given structure. And the resulting structure is hopefully such a config, which actually contains the data. Yeah. Okay. That way, it really shows that we specified the structure, how the Toml correspondingly looks like, but we now have it in Rust, the actual values in Rust, and can use that to for example, sorry. So for example, we could use the TOML file to configure our program. We can specify the various parameter it should run with, and the TOML file just needs to match the structure of the structures we have here. So this is the one approach. And the other approach, sorry, not derive attribute. The other one is to use the value abstraction. So the TOML crate implements some value type, and we rename it here as TOML. In this particular example, we take some TOML data structure and convert it to JSON. And therefore, we also use the serde JSON crate here. And let's dive into the example. So first of all, we have some command line argument parsing in some way. We just check whether or not we are given the first one command line argument. If so, we consider it as the input file. It's just some file path given as provided that we will read as a file, and the content will be considered. Or in the other case, we use IO standard in. We read the data from standard in into a string, and this result will be stored in input. Input is our string variable that will be filled with the corresponding data. So so this if conditional you can see here just allows us to either read a file or use standard in. Okay, and here we have a match statement which actually calls parse onto this string, and we will go into the parse method in the next slide. We match two different cases. Either the parsing was successful and we get some TOML data structure that we can convert, or in the other case we get an error and we will show the error message failed to parse TOML. So in the success case, what we have here is that we take the TOML, use the convert function we will define in the next slide to convert the TOML into JSON, and then we use serde JSON to string pretty with the parameter JSON in order to create a beautiful representation for this JSON. The important point here is that the TOML variable is on the heap, and basically an abstract data structure representing all the different values contained in the TOML file. And also in the JSON case, we have an abstract value where all the underlying JSON data structures are stored. Okay, and I want to briefly talk about input.parse. So we have a string and call the parse method upon it, because here we have some trade awesomeness going on. So essentially the string primitive type in Rust implements a parse method. And this parse method has one type argument, f, which is defined once we know the result return type. Just consider in the previous slide, we had two different cases, okay or error. And in the okay case here in TOML, we actually have we use the TOML variable where, due to the usage of the convert function, we know the type of this TOML variable. Okay, so due to the usage of the convert function, we can propagate backwards the type towards input.parse. So this f type argument we have here on this slide is actually a TOML value. We can derive that due to this, due to how type arguments work in Rust, and they propagate automatically. So due to this example, we immediately know that parse wants to generate a TOML value, and therefore parse is called with the type argument TOML, and for this TOML value, the from string trait will be called. So TOML can decide that we want to implement a parse method which allows us to take some string and convert it into a TOML value. I think that's to some extent also some magic going on, but it really shows some awesomeness that just works because the compiler in Rust is really smart. And also we have a trait. We have trait semantics which allow us to do that. So that's quite advanced, I think, considering the type system. Okay. So I didn't show you the convert function yet. So let's briefly look at the convert function, which just takes a TOML and converts it into a JSON. And in general, we can build it recursively. So we can just make a match statement upon this TOML value. And this TOML value is, of course, an enumerable, which is either a string, an integer, or float, or a Boolean, or array, or table. And we just convert the given value into such a corresponding JSON value. Of course, for a table, we need to consider what's the corresponding JSON value, because we don't have that directly. But yeah, in some way, of course, it's also an object. In TOML, we also have date times. How do you represent a date time in JSON? Yeah, of course, also just as a string. But these are the programmer's decision how he maps these various types. But I think this really is a very intricate example of how that Rust type system is very powerful and allows us to convert between these different values in some way. Given a string, we call parse, and then it just returns the value we are looking for. Pretty neat. Okay, YAML is another file format. YAML is a human-friendly data serialization standard for all programming languages. YAML is a formal standard, well-defined, and which actually with a very large feature set, which also gives it some criticism. And it's strongly typed, so for every value we know which data type it is. It's human readable, and at least to some extent, considering anchors and so on. But in general, it's very human readable, and it also allows us to write comments, which is not the case in case of JSON or CSV. In terms of the file extension, that's a little bit of a debate. So in terms of the designers of YAML, they always specified .yaml as the file extension to be used. But on the other hand, there are also other recommendations for the YML file extension. So that's a little bit subject to debate. And in terms of the MIME type, yeah, again, it's complicated, and there are actually... So in the case of TOML, I mentioned that there are two proposals, either text TOML or application TOML. And for YAML, it's even more complicated. I think there are 4 different proposals currently, and they don't know which one to decide for. Okay, in general, it's a human readable data serialization language. And unlike TOML, which is UTF-8, YAML can actually be encoded either as UTF-8, UTF-16, or UTF-32. And YAML 1.2 is a superset of JSON. That's actually quite important, considering that this was the reason why UTF-832 needs to be supported. Okay, and yeah, indentation is important for the structure, but tabs are not allowed for indentation, and comments use the hash symbol, and they are always single line comments. In general, you can always explicitly point out the data type by using exclamation mark. And if you just write down data line by line and prefix that with the hyphen and a space, then this is a sequence. If you use a key colon value, then it's a map. And you can also use exclamation mark tag in order to annotate entries. It can also be convenient. It allows single quote and double quote strings, but the latter one allows C-style escape sequences like \t for horizontal tabs. And multi-line strings are also possible, and you can use the pipe symbol or the greater symbol in order to get rid of the indentation in the next line or not. Okay, and you also have anchors. So on the one hand, we can use the ampersand and then some anchor keyword, any kind of name you want to choose, to say, okay, I want to address this specific data structure I'm specifying here. Or we can use star anchor in order to reference to it. We will see one example in the next slide. In terms of primitive data types, we have string, with integers, with various bases. We have floats, and we can specify the more advanced values infinity and not a number by prefixing it with a dot that's necessary. And we also have null. What's important and annoying about YAML for some people is that booleans can also be specified with the yes and no keywords. So sometimes you have a map. And you say something like on the left hand, this is the answer colon, and on the right hand side, if you just start writing down values, we can see some example here. If we write down values like Chris on the right hand side, that's just a string. We don't need to wrap it with quotes if it's not a multi-word string. But if it's a no string, the string no, then it actually is coerced into a Boolean, and that's a different data type, and you might get some serialization issues. So yeah, this is annoying. So just to briefly talk about YAML files. In general, so we use these 3 hyphens to start a record, and we use the exclamation mark here to make a tag for this record. And then we always have like key values associations. And interesting is the example lines here, where we use the pipe to create a multi-line string. That's one example. And I also want to talk about these references. So here we have a bill2 key, which has a certain data structure as a value. And this data structure is called ID 001. And later on in ship2, we can actually reference this data structure again and use it again. So all the data given above is copied to the values below. This is a convenient syntax in order to avoid copying the same values again and again. Okay, and the values used in YAML are of course more complex. So if we look at the enum underlying the serde YAML representation is of course much more complicated. So we have no token, we have stream start, stream end, There are also version directives, the tag directive we've seen before, and document start, document end. So in general, the format itself is much more complicated than, for example, JSON. JSON is a lightweight data interchange format, and it's easy for humans to read and write. And it was originally designed as a subset of the JavaScript programming language. And yeah, the MIME type in this case is specified, and also the file extension. And the standard is really easy because they have on json.org, they have these wonderful images. So for example, a white space can either be a space, a line feed, a carriage return, or a horizontal tab, or a repetition of these characters. In terms of numbers, what we see here is that it can be an arbitrary sequence of digits, or it starts with some digits, then dots, some other digits in order to write down floating point numbers. And here we can see that integers and floating point numbers are just mapped to or represented in this number data type, because that's quite common, well known for JavaScript, that we cannot distinguish between integers and floating point numbers. Also important about numbers in JSON is that we cannot write them down in various prefixes, so all of that is always decimal. But we can use the scientific notation, as we can see the E character for the exponent at the bottom. Okay, in terms of strings, we have common escape characters like \t for a horizontal tab, but also // in order to denote a literal backslash. These are strings. Also Unicode code points can be written with 4 hex digits. Value is just any of these is the most abstract, value is the most abstract data type we consider. So we have seen string, number, object, and arrays will follow, but we also have Boolean values like true and false, and null, and at the beginning and at the end, optional white space can occur. An array is just the concatenation of values with a comma and wrapped in square brackets, and objects are just curly brackets, and then we have the association of key and value separated by colons. Okay, now the interesting question is how does serde internally represent such a JSON value? And here we have various cases like null or a bool, where we have an actual Rust Boolean in that case, or we have a number, where we have a number which is explicitly implemented by the certain JSON crate, which abstracts an integer and the floating point value, or we have strings, which are string objects, or we have an array, which are vectors, or we have an object, which is a map, which is also a specific serde JSON type implemented. And serde JSON also contributes this macro JSON, and that allows you, that's macro magic going on here. Null in general is not a valid keyword in Rust, but because we write that down as part of this macro core JSON, we can introduce new keywords whatsoever and interpret that explicitly. And here we have the null value or an object, and the JSON macro will serialize that to such a dynamic value serde JSON value type that we can see as an enum above. Also here some more examples how it's actually mapped and represented. So if we consider some struct w with 2 integers, how does it serialize that structure to JSON? So it's just an object. In that case, we can also define in Rust a structure with two unnamed values, two integers of 32 bits. Then it will be represented as a JSON array. Now it goes more, it becomes more pathological. So here we have a struct with only one field, and this will be serialized directly into this inner value. And if we have the unit struct, so struct without anything contained, then it will be serialized towards null. And here we can see, of course, that we don't have an isomorphism. So there is no bijective mapping between JSON and the Rust data structures, because if we just have a null, if we just consider a null, we don't know which, and we want to map it back to the Rust data types, we don't know which one it belongs to. Okay. All right. There is one more intricate example where we have an enumerable E, where we have various cases. And now the question is, if we have an enumerable and want to serialize that to JSON, how does serde JSON represent it? In general, we take an object where the key denotes which kind of case happened. So either it's the W case or the X case or the Y case or the Z case. And in the Z case, we don't actually have any value, so it will be directly mapped to a string. That's how JSON serde serializes. Serde JSON serializes enumerables. That's actually not according to my plan, because I should have some slide showing missing. I'm using, here we go. Sorry, I'm using my presentation software wrong again. So there are a lot of different topics that I could elaborate on and should elaborate on, but of course the time is limited to prepare such a presentation. In general, I wanted to give an overview to which file formats JSON can be serialized. Also, these two different approaches are important. On the one hand, we can specify the structure, or we can deserialize it dynamically in the heap. These are two different approaches that are important for compiled languages. And I think in general, how serde allows us to serialize and deserialize data is really a convenient approach. The API is well designed. Also, the interaction with files is quite neat in Rust, but we have more advanced topics. So, for example, for standard in, standard out, standard error, of course, we can just use the implemented traits in order to interact with them. But there are more advanced topics, like, for example, here in the third line, you can see TTY detection for colored CLI output. If one program output is piped into the next program on a Unix system, then it can detect whether or not it writes to a TTY pseudo terminal in some way. And if it writes to a TTY, then it knows that it shouldn't use the ANSI escape sequences in order to denote colored output. So this is some important feature that you actually want to do. So if your command line application prints colored output, then you have awkward bytes in there which denote ASCII escape sequences. And if you pipe that, you want to disable that. So you need to detect TTY devices on standard in, on standard out. So that's also a topic that should be discussed, but I didn't have time to do so. Sockets and networking in general, also the final one, Tokyo, and a simple TCP server. I also started to interact with the Rust language server in some way over the TCP server. That was I started with, but it didn't get far enough, so I cannot show you the example. Also, regular expressions are important, base 64, more file formats like XML, HTML, or protobuf. The scraper crate allows you to scrape content. So the idea is that you scrape content from the web, and the scraper crate allows you to access the structure of this website with CSS selectors. That's quite neat in order to interact with HTML. Also, how are URLs represented? Then Clappy is a very important command line interface tool in Rust that is very convenient to use. I think these are in general topics that also belong to I/O, but I didn't have time to go into detail with them. So in general, I'm here at the epilogue, and this is pretty much the end. Sorry, because I used my presentation software wrongfully. I actually skipped some slide before that I also want to show you. I just need to find it. It's about, yeah, this one. I skipped this one. In general, if you want to read a non-UTF-8 file, because everything is by default in Rust UTF-8, and we assume if we just interact with if we convert a string into bytes or the other way around, then we always have this method for UTF-8. But what about non-UTF-8 cases? Then we have something like the encoding RS crate. This one shall be used in order to support other encodings. As far as I can see from the documentation, that actually was implemented as part of the Servo web browser engine, because it explicitly supports, so it exactly supports the various encodings specified by web standards. I think that was the use case to create this crate. And it allows you to just decode the given data in a different encoding towards UTF-8 and then plug it into a string. Because a string in Rust is always valid UTF-8 data. One other question is, what about the cases where we have a non-UTF-8 file path? Because in our example, in all these examples I had, the file path was always a string, but this isn't what a file path is according to what we discussed before. For the file system, it's really just a sequence of bytes. So how does that work? In general, we have a path type in the Rust standard library, and this represents file paths as a vector of bytes. And the fs file open function actually takes a path, but this path is, if you supply a string, this string is implicitly converted into a path, and therefore you can use strings as well for writing down file paths. Okay, so I just wanted to mention that if you have to deal with non-UTF-8 encodings. For example, just to point that out, Golang does not use UTF-8, does not only allow UTF-8 content for the string data type, but any arbitrary byte sequence. So in that sense, a byte slice is the same as a string in Golang. Okay, and now we come to the epilogue, where I have some questions for you to revise the content we had in this session. So the first question we have in terms of the data type, what is a file path? That's why I revised the slide just now. And maybe somebody can contribute the answer to this question. Let me also check in the chat if anybody answers that question. So of course, the point is that it's not a string, but something different. A string in Rust is always UTF-8 data, but here, does anybody have an answer to the question? Okay, so I will solve it myself. So this is a byte array, and one of the traits that occurred is how you can read buffered from some input. So for example, standard in is a certain entity which allows you to read data, and which trait is implemented which trait is implemented so this entity can be wrapped in order to read from it buffered. There is a certain trait we discussed, buff read. Yes, thank you, Gilbert. And which file format allows anchors and references. So one of the file formats we discussed allows anchors and references. And which one was that? Just to remind you, we had the TOML file format, we had the JSON file format, we had the YAML file format. And which one supports anchors and references? So this is the YAML file format, which allows you to denote these with ampersand anchor and star or asterisk anchor. And of course, in terms of the popular Rust library to be used to deserialize data, we have serde. Oh, serde. So, okay. And so in terms of next time, I really want to do the Hacker Jeopardy. So this will be on site this time. And sorry, I screwed up the date. So this will be the 9th month, of course. And that also doesn't fit. Sorry, it's the 9th month and also the 13th. So on 13th of September, we have the next meetup of RustGraz, and I plan to do that on site. And we will do the Hacker Jeopardy, where I will split the audience into a team and then ask Rust-related questions, and you can collect points for that. And it's not about testing your knowledge that much, and merely about trying to understand some source code, what does it do, and also more educational questions where you learn something by looking at the answer. Okay, and in general also, I have some future topics like cross-compilation, debugging, benchmark and tests, and Rust projects I want to show you, and some missing examples and some content I left out. In general, it just should give you the idea that I think 3 more sessions are required. So I can cover the entire content of the Rust book essentially. And then I will be done with my regular talks, and then I will only continue give talks on a non-regular basis whenever I have some interesting stuff that I can show to you. Also, because I have the photo here, it's on site, but I'm not sure we are going to do it in Lab 10. Maybe at university, there is a better location to do that, because we might be able to use some lecture hall where we can fit more people in there and also have more space in order to be more concerned with the COVID-19 situation. So if it happens at TU Graz, Infeldgasse, then you can see on this photo in the middle, you can see the entrance, which is in general locked, but I will pick you up there. If it happens at TU Graz, it will be there. Okay, and I will keep you informed where we will actually make the next meetup. Okay, with that, I'm done and happy about any. Oh boy, I lost the. Now it goes. No, here it is. Now I can switch to the. So this is the final slide. Thank you very much for your attention. And if you have any questions about I/O, I'm here to discuss them with you.